fast that the rate of quantum processes would basically outpace the rate of decoherence, and therefore they would be immune to decoherence. And that's where plasmonics comes into the game. And that's the idea coming back to Ed Purcell, who was a graduate of electrical engineering here in Purdue. And I feel kind of great about that we're using this idea now for quantum photonic circuitry. Okay, so unfortunately, this advances the network. When it comes down to material platforms for various quantum applications, clearly there is a trade-off between interaction strengths, where superconducting qubits probably have superb performance, and coherence time, where one could argue photons are probably the best carriers because they're very, very robust. And of course, there are many other material platforms in between, which also find spectacular applications nowadays, including Gala centers, tractions, and Weber canons. But I would argue one thing, at least as biased as I am, but I'm pretty much sure that photonics would play a very essential role in the future quantum various applications. For very simple reasons, with photons, we package information into signal of zero mass and propagate it at the ultimate speed. And photons are very robust. They don't interact with each other. They interact with matter also very small, for the obvious reason that the wavelength is much smaller than the size of atom or qubit. And to prove the point, I would say two most spectacular applications in quantum, or at least certainly one of those most spectacular applications, is this quantum communication made possible through satellite, experiment done by this Chinese group, and two unambiguous demonstration of quantum supremacy, both related to boson sampling. One done by this PAN group a while ago, and the other one is quite recent, actually, done by Xanadu, where they did this boson sampling within microsecond, and the best computer available, which is in Oak Ridge National Lab, to take 10,000 years to do the same job. Clearly, photons do have certain advantages, but also I should point out that the fact that they are robust, because the coupling of light to qubits is typically small because of the size mismatch, but that's also a double-edged sword, because in some cases you do need coupling. So ideally, you would like to have a strong coupling on demand, but there are also tricks how to enable this, how to make coupling strong when you need it, and to keep it minimal when, for example, you propagate information through optical channels. So when we talk about these photons for quantum technologies, normally what people mention that among strengths and advantages is many degrees of freedom you could use to carry this quantum information, which includes this polarization encoding, path, basically geometrical path encoding, time-being encoding, and orbital angular momentum encoding. And I should add, this is kind of outdated already slide, because relatively recently, my colleague Andy Weider and Roberta Marandotti in Canada showed that frequency domain could be also quite effectively used for quantum encoding. So you see that there are quite a number of different ways to encode quantum information if you use light as carrying information. So I already pointed out that propagation is fast. It's excellent object communication. In terms of challenges, losses, even though they're typically much less than in other systems, it's still an issue. You still have to take care of this. And again, silicon nitride probably is one of the biggest advantages because of the smallest losses. So the interaction is weak, and of course the size mismatch you pointed out, but again, there are ways how to control it and to make it strong when you need it. And yet another challenge, and that's what we'd like to address, is lack of deterministic photon sources, which is very critical for all quantum photonic application. So quantum photonics is actually one of the leading efforts nowadays when it comes down to efforts to bring quantum science to industry. And here I mentioned a couple of companies, but there are many others. So here's like Xanadu in PsiQuantum. So far, what these companies and other researchers use to get single photons is basically spontaneous parametric down conversion, which is a probabilistic process, and that's a problem. If you would like to increase the probability, you of course could increase the intensity of pump, but that would increase probability of getting 2 photons or 3 photons, so that the purity would go down then. And yeah, the additional problem is this, that because it's a probabilistic process, it would require much larger infrastructure to enable this quantum photonic circuitry. And finally, that might be the biggest problem, is error correction. As I will discuss later, error correction arguably one of the biggest problems when it comes down to quantum computing. And so when you process it probabilistic, that also increases error rate. So in that regard, of course, people keep trying to find out appropriate solid-state-based single photon sources. And they are intrinsically deterministic, which is very important. You excite your atom and you get single photon. So they are good in terms of on-chip integration, at least in some cases, but there is challenges to photons operate at cryogenic temperatures, which is a serious limitation. And in many cases, for example, particularly if we talk about quantum dots, inhomogeneity of emitters is an issue. So the people, of course, try very different types of single photon sources based on semiconductor quantum dots. As I pointed out, those typically operate at room temperature, or those based on white bandgap materials, such as diamond, quite famous. And the good things about this on-demand generation, you could do it. Extraction efficiency could be pretty high. You could show indistinguishability. I will talk about this more because it's not sufficient for some applications, such as quantum computation, to have many sources of single photon. They should be indistinguishable from each other. And in some cases, you also have spin properties. And one of the basic, well, of course, that finds many interesting applications beyond this quantum photonic circuitry, which I will be largely focused on. And but at least let me mention, to be fair, this application is related to quantum communication and related to sensing, where various groups have already demonstrated record high sensitivity in detecting, for example, magnetic field, temperature, electrical fields by using these type of sources. But the thing I'd like to emphasize is that why this quantum photonic circuitry is so attractive, because we already have all the foundry. So we basically have everything needed to put it on the chip. We have the materials, we have protocol how to make this single photon sources, this Mach-Zehnder interferometer needed to do these simulated calculations. And if you needed, you could do all this coupling, you could bring nonlinearities for switching. So you could do this filtering, and of course, eventually detection single photon detectors. So I just like to emphasize that the key thing here is really to have good sources of single photons. And that's where we're still not there. And that's why we put our special efforts to develop these single photon sources. So when we try to combine the single photon sources with chip type of circuitry, so there are different approaches. One of those is on-chip integration approach. Like in this case, you basically implant silicon vacancy in this material, or you could implant different type of vacancies. So in this case, you could say about on-chip integration approach. Yeah, another approach is which you could call hybrid, where you basically take quantum dot or nanodiamond and try to couple it to a waveguide. That, of course, has quite a number of challenges. It increases it increases the complexity, and insertion loss is quite significant. So the bottom line is, it would be really great to have material platform with high quality inherent quantum emitters with a material which is CMOS compatible and foundry friendly. So, and that brings me to the silicon nitride. the simple reason why actually it's becoming more attractive even in silicon, it's just losses. It's all about losses. So I put here 1 dB per meter, but I just came from Frontiers in Optics conference. Shalaev reports like 0.02 dB per meter in silicon nitride. So it's really quite spectacularly low losses, which is very, very important to do this quantum photonic circuitry. Refractive index is relatively high, which is of course important for confinement, like in within waveguide. As I pointed out already, this is indeed foundry friendly, scalable, it's the most compatible, and the transparency window is quite huge between blue light and down to 2.5 micron. So, and here you could see some typical losses, propagation loss for different type of materials, and you could see that in this case, silicon carbide goes like down to 0.1, sorry, or maybe 0.2, yes, dB per meter, but it's quite close. And as I said, it's still far from what you, in principle, should be able to accomplish. People still working to decrease losses in this material. So we have this material platform, we have existing foundry. We basically could make millions of different elements. What is missing is single-photon sources, and that's exactly why we were so excited when we first observed these sources in silicon nitride by slightly modifying the standard procedure to make this material, and then doing all these efforts to integrate these sources with circuitry, and that's what I'm gonna talk about. Here is 3+1 musketeers. Alex Silichev actually leads this effort, and Sam did this magic. I mean, fabrication is quite often magic, and he actually made it possible. He found a way how to make this single-photon emitters, and Zach, who is here, did lots of photophysical studies, as Omer helped us with simulation modeling. There are many other group members who now working on this project who joined later, but those studied it. So what are the tricks? The first trick is that why people didn't see single photon sources. It's because of the fluorescence background, out of fluorescent background. If you do nothing, if you make this stoichiometric silicon nitride, then basically you have quite significant out of fluorescent background. And because of this background, you cannot see any single photon sources. And it turns out if you do nitrogen enriched silicon nitride, so then this background decreases by orders of magnitude, truly dramatic. So it basically disappears. And that enables to see really small signals such as single photon sources. Unfortunately, there is a trade-off. If you do this nitrogen enriched silicon nitride, the refractive index somewhat drops, and we would like to have it higher rather than low. But it's still acceptable. It's 1 point, and we are pretty much sure that if you use instead of this high density plasma CVD, which we used in this case, plasma enhanced CVD, then refractive index, as other authors indicated, could be really close to 2. So we're still trying to optimize how to get rid of the background without decreasing the refractive index. But the fact that the background basically disappears is truly spectacular. Now, actually, many groups started to use this trick to get rid of the background. So, but that's one part of the story. The other one is, it turns out that you have to do this rapid thermal annealing to create these single photon sources. And at this, from this stage, basically, I'm starting to speculate. We don't know yet for sure the nature of these emitters, but it looks quite plausible, at least our idea about this emitter. So when you do this rapid annealing, thermal annealing, so our silicon nitride sitting on silica substrate, and it's important. If you don't have silica substrate, you don't have emitters. Actually, we believe that the emission comes from the interface, not from silicon nitride itself, but from the interface, which is actually good. It means that we all have one and the same z coordinate. They all sit in the same xy plane. So, but the idea we have that when you do this rapid thermal annealing, because thermal expansion coefficient for silica and silicon nitride are different, so you create strain, and strain eventually causes these defects. So these defects are most probably, and we're working with material scientists now at Harvard, trying to prove it, and also in Denmark, Technical University of Denmark, that they are actually strain induced, which we find as a good news because you could control strain by many different ways, including electrical. Oops, you're ready. So I was supposed to be on this slide. So, and as soon as you do this rapid thermal annealing, first nitrogen enriched high density plasma CVD, you get rid of this background, then you do this rapid annealing, and then you start seeing this very efficient single photon emitters, which we believe located all here at the interface between silica and silicon nitride. So in terms of their qualities, it's all room temperature measurement. So please remember, and for room temperature is quite impressive purity, quantum purity, 0.08, below 0.1. Basically, lots of emitters have this autocorrelation function below 0.2, and this tells you how pure your single photon emitters, because G2 characterizes that you really have single photon rather than 2 or 3, and ideally it should be 0, of course. So the polarization is linear as expected. The number of photons is quite large, actually approaching 10 million. And they all grouped around these 4 lines. And when you go from one emitter to another, you always have these 4 overlapping lines, which means that the physical nature of these emitters is one and the same. It's broad, but it's one and the same type of emitters. So we of course started to look into the photophysical properties that were done by Zach, who spent some time at Rockwell's National Lab doing these measurements as a function of temperature. So, and actually what was observed that indeed we have this zero phonon line, which is close to well-known the silicon Raman line, and the position of the zero phone line is around 550 nanometer. And of course, the real question is how broad it is. In our case, it's still relatively broad. It's 260 gigahertz, even at 4.2 K. But that's, as we figured out, it's because of spectral diffusion. So we clearly see that there is quite significant spectral diffusion. You see the position of the central line just as a function of time diffuses. And as a result, we have this broadening. And to prove that that's indeed the case, if you measure rather than for 150 seconds, like 2 minutes, if you measure it only for 5 seconds, then you get much more narrow lines. Going down to 30 gigahertz, which is already measurement limited width, so we basically cannot measure more narrow lines. And to find out eventually what is the width of these lines, we're gonna do as next effort photoluminescent excitation spectroscopy, which would allow to obtain more narrow lines, and we would like to see how narrow they are. And eventually, we what we're after is to see whether these single photons could be indistinguishable. And what is required for that, a simple equation probably tells you. So the photon should be emitted with rate higher than the rate of decoherence. Then all single photons would be identical and distinguishable. And the thing here to mention right away, so what we're actually trying to beat, typical rate spontaneous emission is around nanosecond, whereas typical rate of decoherence, basically when phase is randomly changed, is around picosecond or less. So of course it depends on materials, and in this particular case we still don't know how narrow this line could be, and the more narrow line, the longer coherence time, the better. So, but we have in mind a way to speed up the rate of spontaneous emission if needed to make these photons indistinguishable. So this work is in progress, but at least the properties of these emitters look pretty good so far and promising. Okay, in terms of understanding of the nature of these emitters, we started this collaboration with this group from Technical University of Denmark, and their simulations show that if you replace one of atoms of silicon with nitrogen and one of atoms of nitrogen with oxygen, and when you sit in the interface between silicon nitride and silica, that's what could happen. Then you have this type of complex defect as it's shown here. And for this type of defect, what is predicted, you would have this vibronic modes, V1, V2, V3. And what we observe in experimentally, actually, that going from one emitter to another one, the separation of this group of peaks from zero phonon line is around 170 and stays so. Whereas separation between these particular peaks, it's around 10 millieV, and it stays so when you move from one to another. So it looks like that's exactly the nature of this emitter, which we create by applying strain, remember, by when we do this rapid thermal annealing. And also zero phonon line predicted by simulations is around 536, which is relatively close to what we obtained. What we obtained is around 540, 550, depending on the particular emitter. Of course, it's very important to identify the precise nature of this emitter. As soon as we will be sure about this, we probably would be in a better position to optimize the emission from these emitters. So, but what we already did is we successfully coupled these emitters to waveguide, silicon nitride waveguide, like it's shown here. But in this case, we basically randomly choose a waveguide where there is emitter. So we didn't implant it, it's just we choose one where there is a single emitter, this defect. We excite it with through grating. So light goes here, we excite through this grating waveguide, one single mode waveguide. So then it propagates, excites these single photon emitters, and then we detect the single photon emission and obtain that G2 coming from this emitter is still quite low and good, high purity. By the way, this is again room temperature measurements. Stability is good, nothing happened this time. So that clearly indicate that we could successfully couple these single photon emitters to waveguide. And this is perhaps most important part, how really to create these emitters deterministically. And that's a wonderful job that Sam did. He basically made the silicon nitride pillars, cylinders, on the silica substrate. And you just choose properly the diameter. And typically, diameter is around 100 nanometers, 200 nanometers, which is accessible to photolithography, which means it's really easy to make them. And of course, strain, which you induce when you do this rapid thermal annealing, depends on the diameter of this cylinder. So if you really choose properly the size of these pillars, then you basically control the strain. And what was obtained that, as you will see in a moment, that if you choose a particular column like it's shown here, then actually 67% of these arbitrarily chosen have single photon emitters. So what we believe is happening here, the strain is right, and you create single photon emitters. Then because as soon as it's created, the strain is released. And as a result, the second effect simply doesn't appear. As my colleague Evgeny Narimanov put it, strain blockade, because one effect already released the strain, and second one simply doesn't appear. Even if it's really the correct reason, correct understanding, then we probably would be able to, in a controllable way, to bring yield close to 100%. So far, we didn't do anything. We just did it, and we immediately obtained this pretty high yield. I mean, to compare with other single photon emitters, a typically random Poissonian distribution control, and so you usually get only a few percent, and here we got this 67. So if, of course, you could put this cylinder right on top of a waveguide. Here you could see this one single cylinder on top of a waveguide. You could optimize coupling to a waveguide, and this job done by Omer by using this basically inverse design. And of course, you probably cannot do it by using your intuition, but you could design it to optimize the coupling to a waveguide. I mean, if you would like to have simple notation, I think it works like kind of like Bragg reflector, so up to making coupling as strong as possible to this silicon waveguide. So, but the main point I'd like to make here is that for conventional single photon emitters in solids, which you obtain, for example, by doing thermal annealing or ion bombarding. So as I mentioned, they are kind of random. They are controlled by the Boltzmannian process, and the probability to get single photon emitters is about 30% at most, the highest. Here we clearly above that. So therefore, we believe it is a deterministic process, and it could be further optimized. So, and here I'm showing again that the distribution of this G2 as a number of emitters. We checked 57 emitters in a row, just one after another, and you could see that 67% of them actually have G2 below 0.5, indicating they're single photon emitters. And also another important thing, they're all anti-bunched. 100% of them show G2 less than 1. So they're all anti-bunched. So it's really, they have clearly good quantum properties. So this work in progress, and hopefully when we understand better the nature of these emitters and do this optimization work, you will be able to bring BU close to 100%. And then, of course, with the existing foundry, we already started to work with Skywater on this. So you could put thousands and thousands of this type of emitters and do really complex circuitry. So I mentioned already that plasmonics could make a difference for quantum, at least that's what we hope for. And let me explain why. But I guess for this audience, I probably need some brief introduction to the field of plasmonics. So plasmonics is the way to confine light to exceptionally small volumes. So if I have like metal particle, let's say 10 nanometer in size, and if electrons are displaced, and let's see, on this side of the surface, then clearly they would be restoring force. And the electron will start bounce up and down with the frequency dependent on the shape of this particle and the size, but largely on the shape. That because restoring force depends on this. And that's so-called surface plasmon resonance. And the wavelengths could be much, much larger, but all the energy would be concentrated here. That's the idea of this localized surface plasmon. And there are other versions of this localization or confinement of electromagnetic energy. Probably the most famous one is to use so-called gap plasmons. When you have two metallic structures like this silver nanotube and epitaxial silver film, and then you place quantum emitter just in between. So then the energy is concentrated in this dielectric gap, and the dielectric gap in principle could be very small, meaning very strong confinement of electromagnetic energy. Why it's important? Get frozen. Before I get to the point why it's important, since I started to talk about plasmonics, let me mention that lots of ideas related to plasmonics were first, in the later development materials, were first developed actually for random composites, which tend to have quite non-trivial morphology, and specifically so-called fractal morphology. So fractals reproduce the structure of the whole on a progressively smaller scale, either deterministically, like in the case of this fern. You could see that same structures that you have on this scale and on this scale and on smaller scale, or statistically on average, like in the case of this colloidal aggregate of silver nanoparticles. That structure we have been working with when I was at the University of Toronto with Martin Moskowitz. And what we showed at that time, the fractal morphology is actually promotes localization of collective plasmon excitations. Particles are very small, like 10 nanometer in size. And these collective excitations, instead of being spread over the whole sample, are concentrated in these exceptionally small areas, which we refer to as hotspots. And the local field in these hotspots could be orders of magnitude higher than the field and incident field, resulting in dramatically enhanced surface enhanced Raman scattering, dramatically enhanced nonlinear responses, and so on. The thing to point out here, the properties of these random composites are actually defined by structure and geometry, rather than by material properties out of which you build this structure. And this is very much similar to later developed metamaterials. So this idea that you could control optical properties or physical properties more generally by controlling geometry and shape is actually first originated for these random composites, and then was moved to the field of metamaterials. And of course, this number of beautiful demonstrations have been done, which includes metal lens, this hologram, and this non-reciprocal device, switching, and so on. In this case, you design and engineer materials, metamaterials. Met, of course, in Greek means beyond, which go beyond the properties of materials you put that in nature, and that's, of course, very attractive. In this case, it's not Mother Nature which makes this phantom composites, but you engineer that. So, but the point I'd like to make that plasmonics makes processes much faster. And let me first mention this work done we did with your Ployholt in ETH. So, who actually pushes for using plasmonics or nanophotonics quite strongly, and he's, I would say, a leading person in this effort. So here we use this random, gold ring resonator, where in the ring we place electric material, organic material, which changes its refractive index when you apply voltage. So then if you send the signal through this silicon waveguide, if the frequency of this mode doesn't doesn't coincide with the frequency of this ring resonator, then it simply goes through without any losses. Then if you apply voltage in the refractive index, so that now the frequency of this mode matches the frequency of this signal, then the strong coupling light doesn't go through. You clearly have this switching on and off, and it turns out that the extinction ratio is quite high, 10 dB, but most importantly, the speed with which this device operates is in the terahertz rate. And this is the magic number. Remember I told you typical picohertz of quantum processes is the picosecond or 0.1 picosecond. You speed up processes to terahertz rates, 10 terahertz, 100 terahertz, which means it could be, your process could be faster than picohertz process. Even though there is nothing quantum here, but it demonstrated plasmonics is very fast. But let's come back to this Purcell factor. I pointed out that the fact that photons don't couple much to matter is good in terms of they are robust, but to control them, you do need coupling. And in some cases, you need actually strong coupling. And the way to increase coupling was suggested by Ed Purcell. And probably many of you know that the whole size of this paper is one paragraph published in Physical Review. By the way, that paper, he used plasmonic structure, not the electric. That's actually very interesting. But anyway, so what he proposes that if you have a, let's say, qubit atom, which is much smaller than the wavelengths, but if you place it all in the cavity, in this case, dielectric cavity, so since light goes many times between mirrors, so effectively coupling increases. And the increase in coupling is proportional to the quality factor of this cavity, not surprisingly. The higher the Q, the more times actually it would travel between mirrors, and inversely proportional to the volume of your cavity. And most of the groups basically try to use these dielectric cavities with very high Q, such as those based on a defect in a photonic crystal, where volume is small, diffraction limited, but still diffraction limited, and Q could be as high as 10 to the 8. And it works. The coupling indeed increases dramatically. However, the point is you pay the price. The higher the quality factor, the slower the response of your system. So yes, coupling becomes strong, but system responds very slow. And what if you would go the other way? So basically, I still need to increase the coupling, but let's keep Q modest, like in the case of plasmonics. Typical Q for plasmonic structures, such as this gap plasmons or the non-antennas plasmon, it's 100, which means that basically the width would be terahertz. So the carrying frequency is 10 to the 15. If quality factor is 100, it means that the width would be like 10 terahertz or so. It means that the response time would be like 0.100 femtosecond. So it would be very fast. But you still need to increase the coupling. And I could accomplish it by beating the diffraction limit, by taking the plasmonic structure, which could easily confine light down to 5 nanometers. 5 nanometers is 100 times smaller than the wavelengths. And since you have to take it to raise it to the power 3 because it's volume, so it gives you 1 million increase in terms of the coupling efficiency just because of the confinement. And quality factor is 100. The bottom line is I have the same increase in the coupling efficiency, But if I use plasmonic structure instead of dielectric cavity, my system operates much faster at the rate of terahertz, 10 terahertz. And that's the possibility, that's where the opportunity comes to beat the decoherence rate. And that's the idea we formulated in this paper. And now I notice more and more talks here at conference where people started to discuss it. So that basically we make a point in this perspective article saying that, yeah, to protect this coherence, fragile coherence, you actually go to this extremely low temperatures, low pressures, you trap atoms, ions. But what if I simply speed up the process? In this case, the rate at which single-photon emitters. So which single photons are emitted. So then if my photon is emitted before decoherence happens, then it's immune to decoherence. And as I pointed out, typical numbers to keep in mind. Nanosecond, that's typical spontaneous rate, and picosecond, typical decoherence time. So we need per cell factor around 10,000, which is quite achievable with plasmonic structures. So we started to look at particular antennas which could do this speed up, and this is quite famous nanopage antenna. I already mentioned this, like silver, single crystal nanocube sitting at the top of epitaxial silver film. So the thing to accomplish here is actually twofold. You'd like actually to have the gap as small as possible where your emitter is sitting, because it means the volume would be as small as possible, meaning that the per cell enhancement would be as high as possible. But the cube itself shouldn't be too small, because you need to outcouple your photon. If it's or into plasmon excitation, it's converted to photon. If it sits there forever, eventually it still will go to heat. You need efficiently to outcouple it. And for that, since outcoupling is proportional to volume, it's a dielectric effect, it's proportional to the volume, so the volume shouldn't be too small. And actually, what typical calculations show, the gap should be, let's say, a few nanometers, where the size of this cube should be 50, 60 nanometers. And then you do both. You have very strong per cell and very efficient outcoupling before any decoherence happens, or before even loss happens. So you could outcouple photon before even plasmas decay, so meaning it would be loss-free outcoupling. So here our first initial tries, and in this case we would just take nanodiamond with hydrogen vacancy as a meter, pick it up with the tip of AFM, place it on this epitaxial silver, and then use this tip, we push the cube on top of this, so it sits at the edge between this cube and epitaxial film. What we obtain actually, the shortening lifetime by 3,500, which is very impressive, and that actually allowed us to obtain the record short lifetime, 23 picosecond. And G2 does go below 0.5, not much, but still below, indicating that this is single-photon emitter. Most importantly, as Jacob put in, Ethereum did this simulation for us that show if you actually optimize your system. In this case, if you, let's say, the size of this antenna is 60 nanometer, and the size of this gap is like 3 nanometer, then the efficiency of this outcoupling, the efficiency of emission of single photon will be 96%, meaning that really they outcouple before decoherence or before loss happens. And that's actually very, very promising. That's the way we see to get this single photon emitters at elevated temperatures, including room temperature. It's still lots of work to do, but that looks promising. Let me also briefly mention our work, collaborative work on using HBM, because HBM also is known to have good single photon emitters. In this case, particularly boron vacancy. Why it's so attractive? Because it has a spin, and since it's just basically 2D material or quasi-2D material, you could go to very close proximity to a sample which you'd like to probe and measure, for example, let's say magnetic field. And so what we did, we placed this HBM between the silver crystal and epitaxial silver, but first we did simulation, what is the optimal size of this field and where the defect should be located, and it turns out that the optimal thickness would be, for this HBM would be around 6 nanometers, and the defect should be ideally sit somewhere in the middle, and that's what we did. We, I skipped details, so, but we placed this HBM on top of this silver making the shape of a waveguide, which is needed to detect this optically detected magnetic resonance. Basically, it's difference in fluorescence for spin up and spin down. and that's very important, so-called spin contrast. And it turns out that in this structure, you have quite decent ODMR contrast, it's around 6%. But most importantly, if you compare the efficiency of photoluminescence coming from HBN sitting on glass and HBN sitting between cube and the silver waveguide, then we see this enhancement to 150 times. But because the size of the beam, actually, the laser beam, is larger than the size of the cube, and the enhancement occurs only in the area of the cube, when we recalculate it, take this into account, that the actual enhancement is 1700. Unfortunately, in this case, it's not a single photometer because there are many of these defects, but the enhancement is good, and clearly this is also opportunity to do this, to do a good single photometers. All right, so it's time to kind of wrapping up. So let's see what is the vision, what we want to do next with this. I demonstrated this idea that plasmonics could speed up quantum processes, and importantly, a rate with which single photon emitters. But the same idea, of course, could be used for other ingredients of quantum photonic circuitry, such as detectors, such as gates, or for example, a single-photon nonlinearity, or quantum frequency converter. Because remember, all this operates in the visible, and actually, our vision and many others, many would agree with this. It's convenient to do it in visible circuitry, and when you're done with all this quantum simulation, whatever you want to do, then you convert it to telecom and send it through optical fiber. So converting would be important. So we would need, in principle, you would be able to have even close to 100%. You could make here 1,000 and 1,000 emitters. And if needed to speed up the rate with which these photons emitted to make this emitters indistinguishable, then you would place some small, tiny antennas next to each this pillar. And that hopefully would make them indistinguishable. So that's kind of the vision. So what specific things we'd like to do next? We'd like to demonstrate this low-loss silicon nitride waveguide, somewhat different from what we've already done. It's known that if you do it in a symmetric configuration, specifically take a silicon nitride and place it in silicon, embedded in silicon. And if you have it like thin 20 nanometers, then loss could be remarkably low. So basically, energy is still in silica, but the structure is very thin structure, much smaller than the weights to just guide it for a long distance. That's what we're working now on. So another thing which is kind of low-hanging fruit is quantum key distribution. They use a protocol to do quantum key distribution, which is based on polarization, which doesn't require distinguishable photons, but does require the high rate of emission of single photons, and our rate is pretty high. So we hope to demonstrate this quantum key distribution. That's work in progress. And of course, we want to eventually demonstrate this indistinguishability with plasmonic antennas or not by using this two-photon interferometry and on a chip. That's what we're trying to do. And a bigger picture, which is maybe at this point kind of speculation, but that's the way I see this. There are many approaches. Well, I would say that one of the most lucrative applications in quantum is still probably quantum simulation and computation. And in that regard, the approach based on quantum photonics is not profit. There are no memory, but it will allow results solve many, many things. And it's the only ingredient there, as I said, except we would like to get better single photon sources. And without discovering these good emitters in silicon nitride, and with our idea how to speed up the rate with which these photons emitted to make them indistinguishable by using plasmonics we hope to eventually accomplish it. And why photonics? I think it's so important. Because this quantum photonics computation is so-called measurement-based. It doesn't require really gating. The single photon coincidence measurements plays the role of that gating. So it's either one-way computation, it's called, or measurement-based computation. But even more importantly, the biggest problem as far as I see it, and many would agree with me, is actually error corrections. And when it comes down to photons, the error rate is 5 to 6 orders of magnitude less. And keeping in mind that we have all these boundaries exist, it's the most compatible approach which we are trying to pursue. So even maybe not perfect solution, but it could be solution for quite interesting quantum problems. this is just, I'd like to advertise, we wrote this paper with Jen Diane, where we discussed how we see the future of nanophotonics, if any of you is interested. Here is the group, people who really did all this work. And just to let me end up by showing these topics we discussed. Thank you so much for your attention.
So we will open for questions, and if those online have any questions, you can raise your hand and we will get to you, or you can drop those in the chat and we can relay them.
I would see, what is the application of the technology space that you see this fitting into? And more specific, I mean, you talked about generating making Single-Photon cells and launching it into a waveguide, but what is the actual application that you're thinking about here? And then just a little follow-up on that, what would be the metric for technology discussion? When would this be better than something that already exists, so that you can say, okay, yeah, now somebody should adopt this technology?
The short-term goal is to demonstrate first on-chip quantum key distribution. It wouldn't be as good as other approaches, but it would be first on a chip, which I think is important, and hopefully further we will be able to refine it. But having on chip quantum key distribution would be important, and I think we are very close to demonstrate it. The longer term is actually do quantum simulation, because
What's a simulator?
it's related, yeah, I agree, but that requires indistinguishable photons as opposed to quantum key distribution where you don't need indistinguishable photons. And for quantum simulators, we would need indistinguishable photon. That would require more work, create these cluster states, but first indistinguishable states. But that's what we are aiming at, basically to develop quantum simulators on chip. So, and if you would like to, what is different, I'm not saying better. I mean, what people do with Rydberg atoms, ions, I'm not sure we will be there, but it would be on the chip, and I think it could be a big advantage. As soon as we would successfully do it on a chip, then we would get all the power of the existing industry. So those two particular things, which we could think right away. But of course, others as well. Yes, sir.
Yeah, maybe related. So you mentioned that silicon nitride has a large nonlinearity, but then now you're mentioning also that, for example, for the question of the idea would be to use just the single nonlinearity of the single emitter, right? So can you comment a bit about on this, like, where does the nonlinearity come in, or are you just using it?
Good question, and you're right. I didn't cover it. I just mentioned it. People, of course, now is obsessed with lithium niobate, but the truth is, it's not as CMOS friendly. So, and lithium niobate is still a challenge. So, but in the case of lithium niobate, you have Chi2. So here we have Chi3. It's relatively large, pretty good. It's not fantastically large, but pretty good. So the thing we are doing right now, and actually Artyom is working on this, is to do down conversion, which is very easy to go to silicon. For that, we use the silicon nitride-based rings, like Kayla Hala does. Kayla Hala is doing spectacular work now in the realm of classical photonics. I mean, this component chips and for many, many applications. So quality factor is like million or 10 million could be achievable in this ring resonator silicon nitride. So what we want to do to basically enhance this Chi3 dramatically. That's exactly what Kayla Hala is also doing, because of that he got this solid concept. So to create this cluster states you mentioned, because cluster states are very important for quantum simulations. So there are two different options. Either we stay with silicon nitride, and then we would like to use Chi3, but inherent Chi3 probably wouldn't do the job. But if you combine it with the cavity, where basically light travels millions times, you effectively increase Chi3. So Chi3 with a cavity, silicon nitride with cavity, could do a job. And that's exactly what we're trying to do. But in principle, we don't rule out the possibility using also another non-linear material. And actually, it turns out linear, but it's not the best. Actually, the BBO, BTO, like Cyclone uses those material, they have higher current. But the best approach if in steady silicon nitride, and if Artyom would surprise us soon and shows really good Chi3 in these resonators, that's the way to create cluster states, and cluster states are needing to do this photon smoothing.
And this Chi3 is intrinsic to the material, not in defect.
No, that's the point. It's not, it has nothing to do with defect. If place a defect, well, okay, so we couple a single photon to this waveguide, we already did it. So we combine it with a resonator. It has Chi3, the Chi3 dramatically enhanced because of the heavy, it travels many times. And that could be used to generate internal state, cluster states, and down conversion. So that's a key thing which we started to work on. I didn't mention it, but we already have my first preliminary results by using the resonators in silicon nitride.
So a couple of online questions. We'll start with Professor Winful.
Yeah. So can you say something about how excess nitrogen helps to reduce the background emission from silicon nitride?
My short answer, magic. I don't know. The truth is, when it comes down to fabrication, I honestly should say that came as a surprise. But that's now like all groups started to use. For some reason, and I don't know the reason, what the physical mechanism behind that. If you make it nitrogen rich, basically non-stoichiometric silicon nitride, the ground decreases orders and orders of magnitude. And my honest answer, I don't know the physics behind this, and nobody whom I discuss it with would answer this question. But it works.
Okay. Thanks.
Professor Chu, question?
Yes, can you hear me?
Yeah.
Can you hear me?
Yes. We can
Okay.
hear you.
Yes, thank you for an excellent talk, Vlad. I learned a lot of things, and this is almost orthogonal to what I work on. I like to do computer simulations and that kind of work. So I'm very interested in this kind of work because when I was a student at MIT about 50 years ago, my professor told me that photonic computing would never compete with electronic computing because electronic wavelengths is very small, on the order of a few nanometers, but photonic wavelengths are very large. And the components are very large. And I can see from your talk that a lot of your components are still very large. They cannot be made pocket sized, for instance. So I'm interested in if there are efforts around the world where they like to simulate this kind of things. I think what happens in our area is that most of the design and the experiments, we say they can be replaced with computer experiments. I just wonder if a large part of your work can be replaced by computer experiment, or we just do simulations to predict what the outcome would be, and then slowly make things smaller and smaller. That's what happens in the electronic world. In the beginning, we did bulk experiments, but eventually those experiments make to be nanometer size. So I feel that simulations are still very important. I just wonder if you know of other groups in the world who are doing this kind of work. Yeah, your talk is excellent. It opens my eyes to a lot of things.
Thank you. And first of all, it's experiment, not theory. So we didn't say lots of things I showed is already done experimentally. But most importantly, you touched this philosophical question, which sometimes my colleagues in electronics get angry with me. I like to say that the ultra-fast electronics has a special name, and the name for this is photonics. What I mean by this, that with electronics, you're hitting the wall. You never would be able to process information faster than 100 gigahertz. Just because of RC delays, energy consideration, it's fundamental. If you would like to do things truly fast, the only way is to go with photonics. You're absolutely right. Because of the mismatching sizes, the photon wavelength is much larger than the size of the qubit. the interaction is small, and that's a challenge, and your colleague mentioned that was right. But fortunately, there is a solution to this problem, brought up by Ed Purcell, my scientific hero, I should say. He clearly indicated that he could dramatically increase light matter coupling. People have demonstrated now strong coupling, ultra strong coupling. I mean, it's just with light, I mean, by playing all these tricks with confinement. And I guess one of the main messages in my presentation, there are two ways to increase this coupling. Use dielectric cavities or plasmonic cavities. If it's dielectric, it's still diffraction limited. And then, yes, we are talking about structures like 200 nanometers. Why 200? Because, let's say, silicon has, if it's silicon, refractive index 3.5, let's say 1.5 divided by 2 times 3.5, that gives you 200 nanometers. So several hundred nanometers, relatively large. First of all, it's still not that big, but relatively large. However, with plasmonics, you could go truly to electronic-like confinements. These gap plasmons could confine electromagnetic excitation down to 2-3 nanometers. This is the size of transistor, and get this Purcell enhancement. So, and the frequency would be optical. So the world is changing, work. I'm not saying that photonics solves all the problems, but at least it's complementary to the existing electronics in terms of speed. And in terms of coupling, the way to address it, use this confinement, and particularly plasmonic confinements. So you have, as a result, oscillations of optical frequencies, which are specially confined to size, let's say, like 2 nanometer. Something you cannot do with electronics.
Yeah, that is very exciting to hear. I'd like to learn more from you. Okay, maybe we can have tea or coffee together sometime.
You mentioned there's some work simulation in Christian in
Yeah.
GPU that. So did you find any possible telecom kind of emitting effects in silicon nitride?
No, not so far. Of course, we keep looking at this. You're right. I mean, having it at telecom still would be better, and particularly if it would have a spin too. So
I guess recent people found that in silicon. I mean, at least telecom.
yeah, that's those which I know at telecom. They tend to be in quantum dots, for example. They tend to be operate only low temperatures, not high temperatures. So, but I kind of developed this attitude. It's actually more convenient to work in the visible and then convert it to telecom, because there are so many things you'd like to do, and optics at the visible is actually easier. So it still would be great, but the answer is these people at DTU, they are wonderful people. But I mean, he said we will meet in 1 year. He took this how it's called, paternity leave. So, yes.
So maybe a quick question on for the physics of those materials, because when you said it's a magic, then you put more nitrogen in and you lose the background. I would say just simply you have non-radiative pathways. So have you tried to do like various spectroscopies, Raman spectroscopy? Maybe you can see differences in vibration structure of those materials. So basically you're just enhancing non-radiative decay. Yeah, so you're pumping, you have excited states, but they relax without emitting photons, and that has to do with the structure of material, vibration of material. And then the second question, the same kind of way. So you have this defect and it emits light. Can you like spectroscopically see if you can prove this is oxygen involved via spectroscopy? Some kind of characterizations of those.
That's all. The answer to your second question is in progress. That's what we will do. The first one, I mean, photoluminescence looks similar, just completely suppressed background. Raman, of course, we looked at Raman. We see this very strong silicon-dominated Raman lines. In this set, you're right. I mean, in principle, by looking at optically and so on, we should be able eventually to explain it why. But I think pragmatic works, thanks God, we using this. But the other thing I learned that I talked so many times with material scientists, maybe somebody disagree who has more experience. I mean, they just get it from experience, and kind of they know that you do that happens. Quite rarely you see like real clear physics information. It's more like in medicine, you know, that works, that helps.
Mm-hmm.
I don't know about that. I was gonna follow up on her comments, because the material that you're interested in, non-stoichiometric nitride at the top, presumably is amorphous.
Yes, it is.
So you said about using strain to control which emitter is
Yes.
shining. But what do you mean in that case? What is strain? And you have an amorphous, heavily defective amorphous material. You know, maybe there's geometric things that can help you. I would be a little concerned about strain not being being a very local property and not a global property of the film.
Yeah, I don't want to sound like, yeah, it's maybe kind of, you're absolutely right, and of course we did think of this, and that's exactly what we discussed with materials researchers from Harvard. Yes, it's a morphous structure, how strain goes, what kind of defect, like it's local defect, where it's located. By the way, we already did X-ray and we located this defect. It's clearly located in the center of this cylinder, not at the edge, but in the center. That we could see. But how exactly it works, we don't know. And the only question you ask, no questions.
If you want to get to 100% or something like that, that part is it may not be strained at all. I don't know. I have no idea.
But strain is controlled by a pillar. What we have at least so far, and we looked at with X-ray, every pillar has a defect in the center. Well, not every, well, 67% in our case.
Okay, I'm not questioning that. That's fine. I'm saying I'm not sure what the underlying mechanism is.
If I sounded differently, I retracted. You're absolutely right. It's a very good question, and which we don't have answers, but that's what we working very hard with materials.
Yes, my criticism is a statement that if you do figure it out, I could give you a path to even higher.
What I mentioned in my answer to your question is about like nitrogen background. In terms of the strain and effect, it's very critical to understand. And therefore, we go is all the simulation guides and theories. Without understanding the nature of this defect, we wouldn't be able to optimize it. No, I mean, background, okay, we got really thanks, God, but as for defect, we do need to understand precisely what the nature is. And of course, we go into this.
And maybe then you can control the wavelength of emission if you understand the field better. And also, I don't know about oxygen, but if it's an oxygen defect, oxygen is a light atom, it can migrate. So what is the lifetime of those emitters?
Oh, that's stable, nothing happens.
Maybe that's something, I don't know.
So it's
Did you say early on?
We are nearly up to 1100 and then.
That's when everything moves, changes.
Yeah.
And then it
Happens only during this rapid transition, but then nothing happens. So the nature of defect is one of the biggest things to understand, because that's the way to optimize that. That's absolutely true.
All right, let's give our thanks to Vlad again.